For our lesson today, we're going to look at how to graph logarithmic functions. Here's an example of an exponential function in green and its inverse, the logarithmic function, in blue. Notice the line y equals x. These two are reflected over that line, so they're reflected images of each other over the line y equals x. That's going to help us graph logarithmic functions. Notice that the graph of y equals log base b x minus h plus k, general form here with transformations, has these characteristics. Look at our asymptote for the blue function, the logarithmic function. It would be the line x equals h. Notice that we call it h because just like with exponential functions, this is our shift or our translation horizontally, left or right. So this will change our vertical asymptote. Instead of x equals 0, which is our parent function, depending upon what h is, we'll shift to the left or to the right. So we now have a vertical asymptote with logarithmic functions as compared to the horizontal asymptote with exponential functions. Lastly, look at our domain. Our domain is x is greater than h. Remember that domain is all of our possible x values, and that's going to be impacted by our asymptote. So where our vertical asymptote is, we know that we have to be greater than that. We've already examined why this object cannot be negative or 0. Our range then is all real numbers. We can go up forever and we can go down forever. Again, let me point out that this is just the inverse of exponential. You just finished graphing exponential functions, and the opposite was true. The domain was all real numbers, and the range was dependent upon our asymptote, our horizontal asymptote. Let's look at a couple of general graphs. Here's one, log base 2x plus 2. Well, what do you think this plus 2 does on the end? Well, again, it shifts the graph up 2. This holds true whether we have logarithmic, exponential, absolute value. What about if it's in the parentheses with x? Remember, that's a horizontal shift left or right. And in this case, the graph would shift to the left 3. So how do we go about getting our key points for logarithmic functions? Well, we are going to be a little bit tricky, and we're going to rewrite this in its exponential form. So how would this look if we rewrote this as an exponential function? Well, remember, we're going to have the same base of 5. Our exponent then is the y, and this is going to be equal to our object, which is x. From here, it's going to be easy to graph our function. Notice that what we have here is a parent function. We don't have any transformations. Well, normally we would put in values for x, our independent variable, and out would spit the output. For this function, we're actually going to be doing the opposite. We're going to put in y values, and we're going to produce x values. Well, think about our parent function. We know that we tend to use these key points, -1, 0, and 1. We'll continue to use these key points. 5 to the -1 power we know is actually 1 over 5. 5 to the 0 is 1, and 5 to the 1 is 5. From here, we can graph our function. Here are our 3 points. We have one at 5, 1, 1, 0, and 1/5, which is just a little bit to the right of 0 here and down to -1. Now, how are we going to connect this line? Well, in order to do that, we need to make sure that we first draw in our asymptote. Since we don't have any shifts here, we don't have an h value, we know that our asymptote will still be at x equals 0. We'll go ahead and draw that in. So x equals 0 right here. We have a vertical asymptote. And now we can connect these dots. And we can see that our logarithmic function gets really close to the asymptote, but we'll never actually touch it. So our asymptote is at x equals 0. Our domain is going to be where x has to be greater than 0, and our range is all real numbers. Let's try another example. In this example, you can see that we have a transformation. See if you can do this on your own, and then we'll come back and look at it together. The first thing you should have done is rewritten this as an exponential function. Now I know that we have a plus 5 here on the end, but remember, we're always rewriting it in the parent form. This is probably the easiest way. There are other ways to do this, but I find that this is the easiest way to start with the parent function. So we know that our base is 2. So 2 to the y equals x, and then we can use our key points that we are familiar with rather than trying to pick points that will work. So we get 1/2 -1, 1, 0, and 2, 1. These are our parent points. Now we're going to apply our transformations. Well, we know what this plus 5 does on the end. The plus 5 is a transformation. It means the whole graph is going to shift up 5, just like it always has. So we're going to add 5 to all of our y values. So we'll get 4, 5, and 6. Meanwhile, our x values stay the same, 1/2, 1, and 2. How about our asymptote? Well, notice we don't have any transformations moving the graph left or right, so our asymptote is still at x equals 0. Let's go ahead and graph these points. Here's our points. I've made sure to put in my asymptote as a guide, and then I've connected these. From here, we can see that our domain is going to be all the x values that are greater than 0, and our range is once again always going to be all real numbers. Let's try one more example. So for this example, go ahead and pause the video and try this example on your own as well. This logarithmic function has the same base as the previous one, but it could have had a base of 3 or 4. Either way, I'm just writing my parent function. So here's my base, raised to the y power equals x. From here, I can use the same key points that I used last time as a -1, 0, and 1. So I would get 1/2, 1, and 2. Now how about the transformations? Remember, when we have a negative out front, that means we have a reflection across the x-axis, which means that y was negative. How about this plus 4 here? Remember, that means we're going to subtract 4 from all the x coordinates. This is also considered our h, right? X plus h. Anytime we have a change to h, that's also going to change our asymptote. So now we know we're going to have an asymptote at x equals -4. Let's go ahead and adjust our points. So 1/2 minus 4 is -3.5. 1 minus 4 is -3, and 2 minus 4 is -2. Multiplying each of these by a negative, we get 1, 0, and -1. And now we're ready to graph and draw on our asymptote. Notice that after we graph this, we have one end behavior that's going to follow this asymptote. It's going to get very close but not cross. However, the other end is going to continue on down towards -infinity for y and towards +infinity for x. So we'll consider our domain. Our domain is going to be everything to the right of -4, or x is going to be greater than -4. And for our range, remember that never changes, all real numbers. That concludes our lesson today on how to graph logarithmic functions. Remember again that there are multiple ways to graph logarithmic functions, but changing the log to an exponential parent function and then applying transformations tends to be one of the more simpler ways to do this. So at the end of this lesson, you're able to understand that we now have a vertical asymptote rather than a horizontal asymptote, and that our domain and range are just the inverse of the domain and range for exponential functions.